presenting on the removal of heavy metals, lead, and zinc ions from aqueous solutions using a modified orange peel. This is my outline that I'll be telling you. Introduction. Clean water is becoming an increasingly sparse resource. It's becoming an increasingly sparse resource, and it is projected that by 2030, billions of people will have access to safe water, except progress significantly accelerates. Pollution of water by heavy metals is of increasing concern due to its malmagnification, toxicity at low concentration, its adverse effects, devastating effects on the environment and humans, such as air loss by nickel, kidney problem by zinc, teratogenic effects by lead, carcinogenic effects by cadmium, mercury, and arsenic. Several conventional methods are used, such as reverse osmosis, which is not cost effective, ion exchange, which is expensive, membrane filtration, which is time wasting, and chemical precipitation, which generates membrane filtration, which is expensive, and chemical precipitation, which generates secondary pollution. However, adsorption discovered as a sustainable alternative to eliminating heavy metals from water that involve the use of eco-friendly and very cheap biomass. Some of the sources where heavy metals can be gotten, they are generally broadly classified into two. We have the anthropogenic sources and we have the natural sources. The natural sources include the rock deposits, volcanic eruption, sea sprays, and the likes. The anthropogenic sources include from industrial organizations such as mining industries, such as ceramic industries. It also includes agricultural sources such as fertilizers, wastewater, and also domestic sources such as inorganic waste, electronic waste, batteries, used batteries, and so on and so forth. Problem statement. Recent studies have been conducted or suggest that orange peel possesses promising adsorption properties. However, there is need for systematic investigation into the efficiency of a modified orange peel as a adsorbent under varying conditions, which include the contact time, the pH, and the adsorbent dosage. The aim of this research work is to explore the efficiency of using modified orange peel as an adsorbent to remove lead ions and zinc ions from aqueous solutions. These are the objectives as follows: to physically modify orange peels for enhanced adsorption, to characterize the chemical properties of the modified orange peels using LTIR, BDT, TGA, and XRP, to examine the effects of parameters such as adsorbent dose, pH, and even contact time on the adsorption efficiency of lead and zinc ions using inductively coupled plasma vertical emission spectroscopy. Experimental study. My experimental study is as follows. Preparation of adsorbents. The orange peel was gotten from the Alonga market and brought to the chemistry postgraduate lab. It was thoroughly washed with tap water to remove any dirt, and then after washed with deionized water in order to remove any impurities. Preparation of stock solution. Preparation of adsorbent. Immediately it was washed, it was then dried for about 7 days and then after transferred to Federal Industrial Research Lab in Oshodi, where it was hashed. It was physically modified in order to create more surface area for enhanced capacity. And then it was brought out to the lab and stored, sealed. It was sealed so that they can obtain fine particles, and then it was stored for further analysis. Preparation of stock solution. Since the target metals are lead and zinc ions. A stock solution was prepared of lead nitrate and zinc sulfate using standardized methods. Then pressure in a working solution. Working solution was generated from the stock solution. The stock solution is a standard solution of 0.1 milligram per gram. Or rather, 1,000 milligram per gram. Now, the working solution was generated from the stock solution so that I can get 50 mil that will be used for the subsequent adsorption. Adsorption studies. Adsorption studies was properly carried out using the adsorbent in different dosage agitation. This is my result and discussion. The XRD identifies both organic and inorganic components, and then the sharp nature of the spectrum indicates that the cycle is crystalline. For a non-confidence, we need a sample that is amorphous. This is the FTIR. The FTIR spectrum highlights functional groups such as CH at this wave number, CO, CH, and CO, which will contribute to the adsorption process. The presence of these groups indicates that the modified molecule has the necessary chemical functionality to act and react to the metal ions. Thermogrammetric analysis. This shows that the modified molecule maintains stability up to about 350 degrees Celsius before significant degradation occurs. This supports the notion that it will be effective at removing metal ions at ambient and moderate temperatures. This is my BET analysis. BET analysis is to identify or to investigate the pore sizes. This here is showing me that the pore size range, the average pore size is actually 2.647. And it is showing me that this conforms to the pore range of isoporous materials, which is also a good factor for a good adsorbent. Here, this is a plot of my cumulative surface area, cumulative pore volume against pore size distribution. Overall, the cumulative surface area and the cumulative pore size and pore volume increase as the pore size is increasing. However, it was consistent in the graph that the cumulative surface area is higher throughout the experiment, which shows that this material has a larger surface area to volume ratio, which is also a good factor for a good adsorbent. Dosage optimization. This is the actual adsorption result. Dosage optimization. Here is a plot of percentage removal of my lead against the dosage and the uptake capacity. The uptake capacity is represented in blue. It is shown from the result that the uptake capacity for this experiment is highest at 0.5 gram of the adsorbent and lowest at 2.5 gram of the adsorbent. Also, it is also shown that the percentage removal of lead is highest. It keeps increasing as the dosage increases. This is for zinc. The result here is showing the percentage removal of zinc, the percentage removal of zinc against dosage, and also the uptake capacity of zinc against dosage. This also shows a similar trend with respect to the lead. pH optimization. This is where I try to optimize my pH in order to get an optimal pH for further analysis. It was discovered Conclusion. From the graph, it was shown that the optimum dosage of 1.5 gram showed a moderate removal efficiencies of 70.28% for lead and 58.9% for zinc, indicating that further optimization is required. Then thereafter,